All right, Dan, can you hear me?
Yes.
All right, it's my pleasure to introduce Dan Turetsky from the University of Victoria University of Wellington, who's talking on studying introreducibility. Dan.
Thank you. Thank you for this opportunity to speak. I wish it could be in person, but the world, I guess, is still not there yet for all of that. So I'm going to be talking about joint work with Noam Greenberg, Matthew Harrison-Trainor, and Ludovic Patey. This is about coding information robustly. So you've got X, which is an object you're coding information into, a set or a structure or whatever. And information is coded fragilely if it's only in a few places, whereas it's robustly if that information is repeated many times throughout X. And there are a bunch of ways to formalize this. You might look at coarse computability or generic computability or auto-reducibility or introreducibility, which is what I'm going to be talking about. So I'm not going to talk about those first three, but I wanted to mention that there are other approaches to this. So a set is introreducible if it's computable not just from itself, but from every infinite subset of itself. And in this talk, all sets are infinite. I might forget to say infinite from time to time, but there are no finite sets. So let's give some examples. If I have any element of Cantor space, I can form the Decker set, which is the set of initial segments. So if I have the set of initial segments, that's the same Turing degree as the element of Cantor space. And it is the downward closure of any infinite subset. So it's introreducible. My algorithm is if I have an infinite subset of the Decker set, and I'm trying to determine whether a given tau belongs to the Decker set, I search my infinite subset until I find an element which is bigger than tau, longer than tau. And then tau belongs to the Decker set precisely if tau is extended by this element I found. Okay, so great, we can find introreducible sets of every Turing degree. Another approach is this notion of a self-modulus. So a self-modulus is a strictly increasing function which is computable from anything that dominates it. So now if I want to turn this into a set, what I can do is I can make the set whose principal function is f. So another way to say that is I take the range of f. That's because f is strictly increasing. That's what I get. And now any subset of this will be sparser. So its principal function will dominate f. So any subset will compute back f and thus compute the range of f, again, because f is strictly increasing. Okay, so self-moduli give us introreducible sets, and self-moduli occur fairly commonly. Every nice hyperarithmetical set for certain values of nice. So all the 0 to the alphas contain self-moduli. There are a bit more. I don't want to get into the details of that too much. A self-moduli has to be hyperarithmetic. If I have an introreducible set and I just take a computable permutation of omega, then the image of the introreducible set under this permutation will still be introreducible. And then trivially, computable sets are introreducible. So that's some positive examples. For some negative examples, if you take any set y and you join in omega, so splice in omega. So this is write y on the evens and then just put everything, take all of the odds. Then this contains a computable set. It contains the set of odd numbers. So, and since y was non-computable, this is not introreducible. So we can get non-introreducible sets of every Turing degree except 0. So that right there shows us that this is not a degree notion. Another example, if you have an infinite CE set, it contains an infinite computable set. So if I started with an infinite CE set which is not computable, then here's a subset that doesn't compute it, so it's not introreducible. And then Sohr made a very extreme example. He built a set so that, well, if I have X, any X, and I take any A which is made from X by just throwing away finitely many elements, then of course I'm still going to compute X. Right? If two sets differ by only finitely many elements, then they compute each other. And in his example, that's best possible. That's the only thing you can do, because if you throw away an infinite number of elements, then right away you no longer compute X. So this is extremely not introreducible. And we can combine these examples. So to combine the positive examples. So let's think back to Decker sets and self-moduli. If I start with any y and take f, which is a self-modulus relative to y. So just take the definition of self-modulus and you relativize everything to y. So then what I can do is I can take the Decker set of y and then I can thin it to give me back f. So I thin it so that the lengths which occur are the range of f. And again, since f is strictly increasing, that means I can read off f by just reading off the lengths in increasing order. So any subset of this will compute y, just because it's a subset of the Decker set. So any subset of this computes the Decker set and thus computes y. And any subset of this will give me a function that dominates f by looking at what lengths occur. Majorizes f, in fact. So since f is self-modulus relative to y, any subset of this has access to y, and it has access to a majorizing function, so it gets back f. And then once it has f and y, it can compute this set again. So I can combine these two things. I can take Decker sets and self-moduli and combine them. And of course, I can then take computable permutations. So you might ask, okay, well, is this the only way to build an introreducible set? Right? I have these methods. I know I have ways of combining them. Can I build every introreducible set using these tools? So a negative answer to this comes from looking at the complexity. So introreducibility is just naturally pi 1. You write down the definition. For every infinite subset, something, something, something. If we had a positive answer to the previous question, we'd bring that down much lower. Decker sets being a Decker set is arithmetical. Being a self-moduli isn't quite, a self-modulus isn't quite arithmetical, but still there's an argument that we would bring the complexity of introreducibility down much simpler. And that turns out not to be the case. We were able to show that, in fact, introreducibility is pi 1 complete. Now, this statement's a little bit underformed. So usually when we talk about things being complete, we're talking about sets of numbers. Right? The indices for computable well orders is a pi 1 complete set. Okay, introreducibility is a property of sets. So what do I mean when I say it's pi 1 complete? Well, I'll get back to this. Okay. But first, some natural extensions you might define. We have introreducible. So introreducible is saying for every set, there is a Turing functional that, or for every subset, there is a Turing functional that takes that subset and computes the original set. Uniformly introreducible says, well, what if we just reverse the order of the quantifiers? Right? This is very standard in computability theory to say, well, what if we uniformize it? So we want a single Turing functional that works for every subset. Or we might replace the functional with an enumeration operator. So this gets us intro-enumerable. So every subset enumerates the original set. And then we might make that uniform. So again, we have a single enumeration operator which enumerates the whole set. I understand Joe yesterday spoke about intro enumerability. I wasn't able to make it, unfortunately, because time zones are what they are. So, but I'm going to assume that he certainly gave definitions of enumerable, so I'm not going to worry too much about that. So we've got these different notions. How about separating them? So Lachlan built a set which is introreducible, but not uniformly so. So he was able to separate the uniform and the non-uniform. And then it's not hard to separate intro enumerable from introreducible. So start with any y you like. Take something which is CE relative to that y, but not computable from the y. So the jump, if you like. And now let's take the Decker set of y and thin it down to the lengths that occur in X. So if I have a subset of this, then since it's a subset of the Decker set, I can recover y. And right, and once I recover y, I can enumerate x because x is CE relative to y. So this can enumerate, so then I can get back this. And the Decker set, it lets me get y, using only positive information, it lets me get y, both the positive and the negative information about y. So I'm not going to worry about whether x is enumerable or just CE relative to. So this is intro enumerable. It's not introreducible because if you compute this, clearly you compute x, and we just said that y doesn't compute x. I feel like I'm missing a step in that argument. What's the argument why it's not intro? Maybe I need to add the uniformity. Okay, I think I tried to simplify that argument a little bit too much, but okay, it's not introreducible. Yes, thank you. Yes, every CE set has a computable subset. That's great. Yeah. Yeah, so okay, we get any subset of this can compute y. Repeat this fact that every CE set is a computable subset relative to y. So we get there's a subset of this which is y computable. That subset can't compute x because we said that y can't compute x. Okay, that's the missing step. Thank you. Okay. So Jockish introduced this uniform notion. He's the one who said, well, what if we made this uniform? And he was interested in looking at both a set and its complement and said, what if a set and its complement are both uniformly introreducible? And he was able to show that then the set would have to be delta 1, 2, which delta 1, 2 is a lot higher than I usually think of as a computability theorist. I usually don't work that high. He wasn't actually able to build an example, a non-trivial example of this. Solovey improved this from delta 1, 2 to delta 1, 1, and then Siedepun and Slayman improved it actually to computable. Said if a set and its complement are both, well, they were able to remove the uniformity. So they said if a set and its complement are both introreducible, then the set is computable. Jockish was working in the 60s, Solovey was working in the 70s, Siedepun and Slayman were working in the 90s. And then, as far as I can tell, not much was done in this area for almost 25 years. And then we got interested in it. And looking at it with kind of more recent eyes, a natural thing to do is to define reducibilities. It's very common these days to take a property about sets and turn it into a reducibility, a binary relation, a partial order on sets. So let's do that. Let's turn introreducible into a binary relation, which we're going to say, okay, we're going to call it introcomputable. X is introcomputable from Y means that every infinite subset of Y computes X. So the idea is introreducible, saying when X as just a unary relation, saying that X is introreducible, X is playing two roles. On the one hand, it's where the subsets come from. And on the other hand, it's the object being computed. And there's no reason those two roles should be the same. So here we separated it. Here, Y is where the subsets come from, and X is the object being computed. And then we can add the uniformity. There's a single Turing functional which does the job. And instead of compute, we can do CE operators or enumeration operators. And then we can get back the unary properties by just reflexivity. Introreducible, a set is introreducible precisely if it's introcomputable from itself. So if you think about it, a uniform operator, CE operator or Turing operator for intro CE, intro computable, since it has to work not just for the set Y, but for all subsets of Y, all infinite subsets, it can never believe any negative information it sees. If it's told this element is out of its oracle, well, that could be an element that's truly not in Y, or it could be an element that's in Y, but just not in this particular subset. So negative information is useless, as expressed in this lemma. If X is uniformly CE, intro CE from Y, then it's because X is uniformly intro enumerable from Y. There's a reduction that only uses positive information. And then from that, we can get the same thing for computable. Right? Because X being computable from Y, or from a subset of Y, is the same as X and X complement both being CE, which by what we just said is the same as both being enumerable. So the operators, Turing functionals or whatever sort of operators we're looking at, can really only use positive information. All of this is for the uniform case. I imagine there are counterexamples to the non-uniform version, though I don't know of them off the top of my head. But it seems likely, just because uniform is generally nicer behaved. Okay. So let's go back to completeness. What do we want to do? We want to do pi1 completeness. So given a computable linear order, we want to build a set X, which is uniform, if we just want to do completeness for introreducibility, we just wanted to make it introreducible if the linear order is well-founded and not if the linear order is ill-founded. I don't know if you can hear the rain. Sorry, I'm speaking up because of the rain. We'd like to actually handle completeness for both the uniform and non-uniform simultaneously. So we'd like to make something where if linear order is well-founded, it's uniformly introcomputable, introreducible. And if it's ill-founded, then it's not even non-uniformly introreducible. What sort of set can X be? Well, X can't be computable because every computable set is introreducible, right? And then we wouldn't have the freedom to depend on L. And it can't be CE. As we said, a CE set is introreducible if and only if it's computable. And saying that a CE set is computable is low complexity. It's like sigma 3 plus or minus 1. And we're trying for pi1. So it can't be CE. So the simplest X could possibly be is co-CE. So that's the sort of set we'll build. So formally, this is a statement about the set of co-CE indices for introreducible sets. That's a pi1 set, pi1 complete set. So we're going to incorporate well-foundedness. Let's just try to get a sense of where the well-foundedness sits. So suppose X was uniformly intro-computable from Y. Then we've got a witnessing function phi. Then for any n, I can make this tree of increasing sequences, but let's take increasing sequences from Y. So each finite increasing sequence from Y gives me a subset of Y, its range. And I can plug that subset into my functional, and I can ask, is this enough to make it converge on input n? And I'll snip off all the places where it does converge. So what I'm left with this tree where it diverges. And by standard use assumptions, this is computable from Y. This tree has to be well-founded. And if there was an infinite path, then that path would give me a subset where this functional never gives me an output for n. So here's where the well-foundedness sits. We want to make our operator, the trees that come from our functional, look kind of like this. And since we want to make it introreducible if and only if L is well-founded, really what we want to do is we want to make the trees have rank L. So then if L is a well order, this works, and along any subset, the functional gives me an output. And if L is not a well order, then there's some infinite decreasing sequence. There's some path through the tree where I never get an answer. Okay, so how are we going to do that? We're going to look at the Decker sets. So the Decker set, let's think about it's introreducible. In particular, any string tells you all the information you could want about shorter strings. And if I know that sigma belongs to the Decker set of Y, then I immediately know whether any shorter tau belongs to it or not, because it's precisely if it's an initial segment of sigma. So let's keep that idea going. I want every element to tell me about all the previous elements. So how could I do that? Well, I could have a computable function that takes an element and gives me a finite set. And so f of A is A's guess. A is guessing that the set up to A looks like f of A. And if A belongs to X, then that should be the correct guess. Well, two problems. First of all, that's too simple. Having a computable function, X having a computable function with these properties is, again, low complexity. It's sigma 0 something. And we want pi 1, 1. And also, this is not including L. So the way we want to incorporate L is we want to say that not every element, not every element is guaranteed to be correct about its guesses. A has this guess, f of A, and f of A might not be correct about X, even if A belongs to X. So instead what we'll do is, since we're assuming our linear order has domain omega, if you give me a subset, I can start just going through that subset, and this might be a decreasing sequence in the linear order for a little while, but if it's a well order, eventually I have to go up. And that's when guesses have to be correct. So if you give me two elements A and B, where B is before A, both in the usual ordering on omega and in the L ordering, then f of A's guess has to be correct up to B. So now, how can this work? So how do I get my reduction? If you give me an n and you want to ask, you give me a subset of X, and you give me an n, you want to ask, does n belong to X? Okay, I search my subset for some element bigger than X, call it B naught. And then some B1 bigger than B naught, and then B2 bigger than B1, and etc. This is an increasing sequence in the usual omega ordering. it can't be a decreasing sequence in L if L is really a well order. So eventually I have to find BI, which comes before BI plus 1 in L. And at that point, I know that f of BI plus 1 has to be correct up to BI. So it has to be correct about n. So that tells me what n is. So I have to, okay, I pick an f which is sufficiently general. And I say, okay, I'm going to commit to this method of decoding, this kind of reduction. So I'm going to have to commit to an x that satisfies this. And then I still need to try to diagonalize, right? So if L has an infinite descending sequence, that's an infinite subset of X, which this reduction fails for, because I'll never find a B less than A that satisfies this. But of course, there might be other reductions. So I have to diagonalize against other reductions, and there's work to do. But that's the general idea. Okay. So what about boldface completeness? So we have a process, a computable process that takes a computable linear order and gives you a set in a co-CE fashion. So it takes L and gives you X. We could just run that we could relativize that. So now you give it any linear order and it spits out an X in a co-CE fashion relative to that linear order. And we can ask, okay, does this do boldface pi-1 completeness? So here we're looking at Borel reducibility, and this is about sets of reals, sets of sets. So this is like standard M reducibility, except instead of computable functions on numbers, we're looking at Borel functions on reals. So this process I described, okay, take L, give X in a CE fashion. That's not a continuous reduction because X is given, in a co-CE fashion, because X is given in a co-CE fashion. It is a limit of continuous functions. So it's Borel. It's a Borel process. And if we just do everything relative to the linear order that we were given, there's a slight detail to worry about. So we run that whole construction relative to L. And if L is ill-founded, then we diagonalize against every possible, we diagonalize against being introreducible even relative to L. So that's certainly not introreducible. Great, that's handled. What if L is well-founded? Well, now we want to build something which is truly introreducible, not just introreducible relative to L. So we want our reduction not to need L's help as an oracle, but that reduction that I described sure does need L to work. So the easiest way is to make sure that actually X uniformly intro computes L. So the X I get immediately on any subset of it immediately gives you L, and then you have L to do everything else you want to do. And the easiest way to do that is just to take the Decker set of L. So we build our co-CE set inside the Decker set of L, and that gets us pi-1 completeness. Okay, different line of inquiry. So if I have an intro computable or intro enumerable set, then I know that every subset of it is at least as strong in whatever sense
Dan?
is appropriate. Yeah.
Can you go back a slide a second?
Yeah. What's up?
So you're given L and you build X, right? And you just want to have that property. I was just confused.
Yeah. So yeah, this is a process. You're given an L, in this case, as an oracle, and we want to build X, in this case, kind of co-CE relative to L. So we build it as a co-CE subset of the Decker set of L.
So it's just an additional requirement you add to your construction.
Right. Yeah. We just, in order.
Okay. Thank you. Thank you.
Yeah. So just, backing up. This part here, we want this to not have to be relativized to L. So we cheat by making sure that L can be gotten from X. Okay. So what was I saying? So, right. Every subset of X is of degree at least X, but by here I've done a counting argument, but there are plenty of other arguments for why, in fact, there are lots of subsets that are stronger than X in Turing degree or enumeration degree or whatever sort of degrees you're looking at. So, okay, can we reflect this increased strength by turning one reducibility into another one? And yes, we can, right, suppose X is intro computable from Y. Then we can make this uniform as long as we're willing to pass from Y to a subset of Y. And this is a very kind of standard trick. This is the forcing argument that fails. So, right, this is a standard trick to uniformize things. You do a few steps of a forcing argument, and then you stop, and you're done. Okay, so we can uniformize the intro computable. You can do the same thing for the CE reduction, and then that immediately implies the enumeration reduction. Just because enumeration reduction is stronger here, and I said these two, it's equivalent here. So, so yeah, great. We can get stronger by passing to subsets. Okay, how about a different way of getting stronger? Can we go from enumerable to computable? So go from intro enumerable to intro computable. How might we try to do that? So suppose I have a Y computable enumeration of X. One thing I can do is that enumeration has a settling time. Basically, if you take that enumeration and you take a sufficiently fast and combine it with a sufficiently fast growing function, you will compute X. So what I might do is then say, okay, take a subset of Y, which is sparse enough that its principal function majorizes the settling time. So now Y enumerates X, every subset of Y enumerates X, every subset of U enumerates X. U majorizes the settling time. Surely that means X, U can intro compute X, right? Or on the other side, what if I don't, instead of shrinking Y, what if I try shrinking X? So recall every CE set contains an infinite computable set. This is one way to argue that, is I've got this enumeration, I take all the elements that are enumerated before anything bigger than them. This is Y computable. So if all the subsets of Y enumerate X, then surely that they must all compute Z, right? Well, no. And the problem is, yes, all the subsets of Y compute X, or enumerate X, but they don't all enumerate X in the same order. Different subsets can have different enumerations, and those two approaches just there depend on the particular enumeration. So in the first case, we said, well, what if we take a sparse subset so that we majorize the settling time? Well, that sparse subset has a different enumeration, and that different enumeration has a different settling time. So we majorize the old settling time, not the settling time we should have majorized it. Or on the other hand, different enumeration.
Is there a typo in the first statement of the theorem? The U should be a Z?
Yeah, or the Z should be a U, one of them, yes. This U and this Z should be the same set. Yeah, thanks. Yeah. Okay, so that on the other side, right, again, different enumerations. So let's look at the definition of Z. This definition depends on the particular enumeration. So different enumerations are going to get different subsets. So if Y uniformly intro enumerates X, then yes, every subset of Y computes a subset of X, but they don't all compute the same subset of X necessarily. Okay, so we can't shrink on the right, we can't shrink on the left, but we can shrink on both sides. So if y uniformly introenumerates x, then if by shrinking appropriately on the left and on the right, I can turn that into introcomputability. And also, if x and y were the same set, then we can assume that u and z are the same set. So what this tells us is a uniformly introenumerable set. So this is, again, it's a unary operator. If a set is uniformly introenumerable, then it contains an infinite uniformly introreducible subset. And I want to give a bit of an idea of, I'm not going to give the full proof, of course, but I want to show some of the ingredients that are involved here. So first of all, I've got my enumeration operator. Since this is uniform, I've got this one enumeration operator that works for every subset. And I can define basically the same tree. I look at increasing sequences of elements from Y, and each of them gives me a subset of Y, and I say, is that subset enough to enumerate N? And if so, print it off, and by standard use assumptions, this can be a Y computable tree. And so we get that this is well-founded if and only if N belongs to X. Okay. Well, turns out I don't quite want to look at tree rank, right? It's well-founded, so I kind of want to look at the ranks, but tree rank is not quite the right thing. I want to look at labor rank. So labor rank is like tree rank, except, so with tree rank, the rank of a node sigma is the supremum of the ranks of its children plus one. With labor rank, instead of supremum, it's limit supremum. So finitely many children having big rank isn't enough to give you big rank. You need to have infinitely many children that have big rank. This is just more robust to finite changes. If I remove finitely much of the tree, that's not going to change the labor rank of any of the nodes that remain. With tree rank, if the rank of a node is infinity, that means that that node can be extended to an infinite path. With labor rank, if it's infinity, that means that node can be extended to an infinite bushy tree, an infinite bushy tree of infinite bushiness. So, okay, so we look at these ranks. Why do we need to shrink on the left? Well, we want to shrink to make these ranks either be constant or be strictly increasing. So, right, for every element of X, this is well-founded, the tree is well-founded. So for every element of X, we get an actual ordinal as the rank. Shrink down so that the element to Z, so that the elements, the ranks are either constant or increasing. Okay, now these ranks, it'd be great if they were computable ordinals, right? But we don't, there's no reason to expect that. These are Y computable trees. Even if they're well-founded, there's no reason the ordinal should be a computable ordinal. It should just be a Y computable ordinal. So, okay, we can pass to this subset of Y, so the principal function, we'd like the principal function to kind of give us a clock for well-foundedness, because the idea is I've got a tree and I've got, so I've got a subset of Y. I can just make the sequence, the increasing sequence, which lists that subset, and see, do I ever get, do I ever enumerate N? If so, N is in. If not, well, I'd like to have some idea of when I can say, okay, I'm done searching, N is out. If these were computable ranks, I could kind of, I could make a sparse enough function that basically it would be kind of like enough jumps that it would let me kind of get a clock for saying, I'm pretty sure I'm done searching. Since they're not computable, I can't. What I have to do is I have to use them as each other's clocks. I have to play the trees against each other. Obviously, I'm eliding many details, but this is the basic idea of what's going on. There's some of the ingredients of what's going on. Right. Thank you.
Thank you, Dan, for a nice talk. Nice results. I'm gonna do something on standard. Anybody in the chat want to ask a question? Just make sure I get my chat up. Nope.
Only a few of us.
Anybody locally? I have a question, but okay. Dan, go back to that theorem the last theorem you proved.
This one.
Yeah.
Yes.
So if you have a relation, say X and Y are Taurian equivalent, could you make it U and Z being Taurian equivalent, or just what kind of relationship do you think you could preserve and make this happen?
X and Y are Taurian equivalent. Can we get
if they remain arithmetic in each other, for example?
So certainly I should mention the U and the Z that we get are delta 1, 1 in Y. In X join Y, but since X is a numeral from Y, it just means delta 1, 1 in Y. I don't know. Yeah, could we? Yeah, if we had additional relations between them, could we preserve that? I don't know.
Okay.
One thing that we can do, though, so here, I said it's not enough to just shrink on the right-hand side. If we have some nice properties, like if X was itself intra-enumerable, we don't even need uniform, then we could just shrink on the right-hand side, for example. Or if Y is low for omega 1 CK, then because then we don't have to worry about that ordinal business I was talking about, then it would be enough to just shrink on the right-hand side. If they're Turing equivalent, well, okay, so if they're Turing equivalent, then since any subset of Y can enumerate X, then every subset of Y can enumerate positive information, negative information, but they can enumerate Y. No, maybe that's not true. Sorry. No, I don't have a straight answer. Sorry.
Okay. Well, thank you. Thank you for the interesting talk. Ted, I'll bring you the mic.
Hi, Dan. I don't have a question, but I just have a comment. You attributed a results to David Siedepin and me.
Yes.
That result does appear in a joint paper, but the theorem is entirely due to Siedepin.
Oh.
So it's I didn't have anything to do with the proof of this. It's, I was tempted to assume credit, but it's all David Siedepin's work.
Gotcha. I knew it was based on his Ramsey theory work, so I didn't, but yeah. Thank you.
In the Notre Dame Journal of Formal Logic, too. More questions or comments? Okay, well, let's thank Dan again. This time he could hear us.